All right, I guess, yeah, we can go ahead and get started. So welcome everyone. Um, yeah, Sammy has graciously agreed to do a technical walkthrough of Prefect. I think a lot of people will benefit from this. I think the motivation for this was because we had some new folks join the GitLab team. And so I thought it'd be useful to kind of do a walkthrough of just how it works. And I know that, we're talking about kind of re-architecting it, but I think it still would really benefit everyone to understand how it works now. So thank you, Sammy. And there's a doc in linked from the calendar invite, and there's the question section. And so as we go through this, if you have any questions, feel free to put them there. And then, yeah, I guess if we have time, then Sam, we could address them at the end.
Yeah, absolutely. Questions would be more than welcome. Yeah, it's going to be fairly freeform. Oh, we are missing some access on doc. You can share.
Yeah, I'll give you access. Hopefully, I'll just.
So I think everyone at GitLab should be able to access it now.
Yeah.
And
yeah.
The link is here. Yeah, so it's going to be fairly freeform. I thought that maybe we would just first look at how it's sort of how Italy and Prefect fit into the architecture, and then basically go through the request path, and then have a look at maybe in more detail about the different processes and what sort of background operations we have there. So I'm going to share my screen to start with that. And you can most likely see my screen now. So basically, yeah, what Prefect and GitLab do for GitLab is basically that we, of course, store all the Git repositories, provide basically just RPC access to Git repositories. Previously, GitLab was part of Rails app, then it was later split out from there as a separate Rails service, and I think then it was begun being rewritten in Go, and currently we're at the point where most of the things have been migrated. We still have basically a Ruby card in GitLab. Prefect was then later added on top to act as a coordinator and routing proxy for clustering GitLabs. And most of the clustering logic then lives in Prefect itself. So the interface that Prefect basically exposes to GitLab is the same as GitLab. It's all of the protos we have of the various services. Prefect transparently basically implements these and adds clustering logic on top. Most of them are implemented sort of in a generic manner where we just proxy to GitLab and records what operations are being performed, which replicas are accepting those operations. But there are some which are handled by Prefect specifically, namely the Prefect specific services, and also some operations that actually have difficulties being just routed generically. For example, remove repository is one of them. We'll get to those later. So each Prefect can have multiple virtual storages. Virtual storage is basically the interface that GitLab sees. Just each GitLab has multiple storages by default, like can support multiple storages. Prefect then virtualizes those storages by providing, again, a single interface to GitLab, which may actually be multiple GitLabs in the background. So GitLab is illustrated here. Each of these would be sort of physical storages, whereas with GitLab cluster, you show a single storage to GitLab, and in the background, behind that abstraction, you actually handle the logic of routing the requests to the correct locations and replicating the repositories. So the main operation is basically acting as a proxy that records operations. that are being done, creating repositories, writing into them, and also routing requests correctly to the replicas based on the information which replicas are up to date, which not. There are some other responsibilities that it also does then, basically related to replication. So if you add more nodes, the cluster Prefect will then, of course, manage all the replication logic in the background. But to start off, I think we could start going through the request flows and the type of requests we have. So in the lint proto in GitLab repo, we actually have the different types laid out that we support. Basically, there's mutator accession maintenance. The maintenance is something that is going to go away soon. It's mostly things that don't really change the data as the user sees it, but internal operations. This used to be like, for example, garbage collection, repacking, things that improve performance, but don't really actually make any visible data changes to the user. This used to be handled by Rails. They're going to go away. They're going to be basically moved into GitLab entirely. So this type will also disappear in the future. Accessors are anything that simply reads from a repository. Basically anything that shouldn't require replication. And mutators are anything that perform anything that changes the state of the repository that we should actually replicate. There's also a scope that is used for proxy. Storage is anything that would be a storage-wide operation. We don't really have those anymore. Back in the day, we had namespace service, which was basically renaming storages, directories in the storages. It's not used anymore. So the storage-wide scope is actually also sort of something that we're going to get rid of soon, I hope. So most of the operations are actually basically scoped to a repository or handled by Prefect directly. And for the mutators, there's one more distinction, which is that some of the mutators are handled in a transactional manner by Prefect, where all of the changes are performed at multiple GitLab nodes at the same time, and the GitLab nodes vote back to the Prefect to confirm that they are making the same changes. And if so, then they are applied. Basically, I think we have a graph here that shows it somehow. Not here, but actually here somewhere. So this is the design HA doc we have in the repo, which mostly contains all the like technical documentation. So basically, in these cases, yeah, this is the right graph. So a write comes through, it goes to both GitLabs, and then they will vote back to Prefect, and Prefect records the changes if everyone voted the same. We can see the RPCs that are actually transactional right now. That should be the majority in the coordinator. So this is Prefect coordinator.go, contains a static listing of RPCs that should be handled transactionally. Most of the RPCs don't require anything specific to actually support transactions. They're implemented generally via the reference transaction hook of Git, which gets invoked every time there are reference changes being done. So if the RPC is just changing references, then it most likely automatically or like works with the transactions. There are some special cases, which are usually operations such as config writing, which is not a reference update, where there is usually a different voting approach. But I think, and then, yeah, then there are some which we have transactions disabled. Some of these are handled by Prefect. For example, rename repository has a separate handler in Prefect, basically here. And so it doesn't get proxy through. Will, you have something?
Oh, yeah. So I was just asking or wondering, so when you do a transactional vote, if the secondary comes back with a different result than the primary, that doesn't fail the push or whatever action is being performed? Does it still go through on the primary, assuming the primary was okay, and then we just replicate lazily, or what happens in that scenario?
We can go through it in more detail when we go through the writes, but what will basically happen, we require the primary and half of the secondaries to accept. Well, one of the secondaries to accept. We basically require half of the primary has half of the votes. So primary and one secondary to accept to actually go through. Or should, yeah, let me actually check. We have it somewhere. So I'm actually wondering if we did change it. But the what should happen is basically that the pride does go through, but the secondaries that voted separately, differently would get replicated to afterwards. And they won't be picked up for the next transaction before they are replicated.
Makes sense. Thanks.
Yeah, I'll just register a transaction, I think was the. So we can actually here in the coordinator, we can see the code that is setting up the quorum. So secondaries. Yeah, so actually it should go through based on this. So the primary has more votes than all the secondaries. So
I see. So just the primary by itself would be enough.
Yeah,
okay, that makes sense.
The primary can go through without secondaries.
Okay. Thank you.
But yeah, so the way the proxying is handled in Prefect is basically anything that is not explicitly registered in the gRPC server Prefect goes to an unknown handler of gRPC server, which then contains the proxy logic. So anything that is registered actually in the gRPC server will skip the proxying and just be handled directly in Prefect. This is where we set up in server.go in Prefect, the gRPC server, and we are also setting up the unknown service handler here, which will walk in soon. And we can see that there are some special RPCs that are registered that are being handled by Prefect directly. So these are not proxied again. Prefect has a handler for all of these 3 RPCs, plus some other services that are not being sort of intercepted from Prefect like Gitali, but rather handled directly in Prefect, which services basically that Gitali doesn't even expose. Once a call goes through, it gets it basically goes into the unknown service handler, as it's usually for an RPC that is not registered, and that's when we jump in the proxy package. It's vendored in the proxy code is vendored in Prefect here. We go into the handler, which takes the call, and this is actually the proxying logic here itself. How Prefect proxies is basically does frame-wise proxy of the request. So we don't necessarily proxy a full gRPC request always. It's frame by frame. So you should never end up in a situation where one of the replicas is slow and the others are like proceeding faster in the proxy logic. But all of them should be pretty much going at the same pace. The proxying code here, I think, it gets a bit complicated with the concurrency. So there's, I think, not too much point walking through here. It's probably best to look at it offline, but basically the logic here is that we receive the write from the, or any sort of like the write or read from the client. We proxy it to the primary and the secondaries at the same time. And we then return the error that actually comes back from the primary, or if there is an error from the secondaries. To know actually where we are proxying the calls, there's a director which it gets invoked before. I think it actually comes in the unknown service handler, which is not here. But the director is That's a good question where it's actually invoked specifically. It's somewhere in the director, register service, director, streamer, transparent handler. Yes. So the director is invoked here, right in the handler. So the first step is basically invoking the stream, the proxy, I think it's called the stream director, right? The stream director. What it does is it basically, that's the hook point for Prefect to tell the proxy where do you actually want to send the calls. And the director is called from here, and we then go into the coordinator. And the coordinator contains the stream director as well. First happens, basically, we start looking up by methods, whether they are accessors or mutators. And we have a separate package here in the proto registry, which contains basically logic to read the annotations we have on the protos. We have basically every RPC is annotated with accessor or mutator. And based on that, the director then decides the routing method. So most of them will be going to direct to repository scope messages, which then further splits into repository specific accessors, mutators. Looking through the accessors, it's a bit simpler. What happens is that it mostly just actually invokes the router component of Prefect. The router is an interface, basically, that provides the director with the routing information. It checks basically that the nodes we route the requests to are up to date and they are healthy. So the logic is these days happens mostly in the router per repository. So for example, in the case of a repository specific repository scope accessor, we would end up here. So we can see here it checks the node healthiness first, finds the storages that are up to date, picks a random one of them, and returns the route. And then based on this route, Prefect rewrites the message. So as we were sort of looking at the graph in design HA, or rather documentation, the storage that is exposed to Rails is different from the actual names of the storages on the Gitali nodes. So for example, one of the Gitali nodes that are part of the cluster may have a storage called Gitali 1, the other one has Gitali 2, but Rails doesn't see these internal storage names. Rails only sees the external storage name, which is storage 1 in this case. So all of the messages that come in are addressed to this external name, storage 1. And in order for the Gitali nodes to actually know which storage the request should be routed to, Rails Prefect will basically take this name, see which storages are the internal names that are used for that Gitali node for this virtual storage, and rewrite the gRPC message. So the message is here, the repository. So each of the repositories carry the storage name and the relative path, which is how the repositories are identified currently on Gitali. So basically just saying sort of which storage location, usually this just refers to a single disk. And then the relative path, which is actually the disk path of the repository inside the storage. So Gitali Prefect just transforms the storage name first to the internal storage name of the Gitali, and also the relative path, but I'll get to that a bit later. With the accessor. Yeah, so with the rewritten message then, that's basically remaining to do is that the proxy is given back the destination it should proxy to, and then we sort of return to the handler. So here are the params. The params then contain the routes. For example, here the params contains primary, and the proxy does the proxy logic of opening a stream to the primary, opening a stream to the secondary is here, waiting until all the messages are proxied and the response is returned. That's the life of a read through Prefect. Do you have any questions about the reads? Wonder if I'm on going like on a too high level or Then if not, I'm gonna proceed to writes. So the writes follow mostly the same pattern. A write comes in, it again goes to the unknown service handler of Prefect, which directs it to the handler of the proxy. And the proxy again invokes the same director that we just saw for the reads. And the director then looks at the types again. It sees that this is direct repository scope message, goes again there, and this time goes to mutator. So mutator is basically the type for the writes. And the mutators are routed in a bit more involved manner. So there's two different types of mutators. Let's go through first the write. Write into an existing repository, that is. And again, once we get to the mutator stream parameters part, which is routing a mutator, it first consults the router of Prefect for where we should actually route it. And this part, route repository mutator, is basically the routing method for routing a write. It mostly does the same logic. Writes are, so whereas the accessors are always routed to one up-to-date node, the mutators, they always have to go to the primary. And then this also involves the primary election logic in Prefect. So what happens is that first we check the healthy nodes here, resolve the repository ID that Prefect identifies the repository with from the external virtual storage in the relative path in the repository. Resolve an additional path, which we can get to it later. And then we see which node is the primary. If it's all set, we'll just continue forward. Again, building a route and eventually returning back from the routing method. The additional thing that we also consider for mutators that we don't really consider for accessors is the assignments. And the assignments are basically saying that whether a node should be hosting a replica. Imagine you have 100 nodes. Not all of them necessarily have to contain a replica of a repository, so the assignments are saying where they should go. Otherwise, if we didn't sort of have assignments, we don't necessarily know where we want the replicas to be. So this is saying the constraints of which nodes are actually expected to contain. So there could be, for example, 5 replicas of a repo, but only 3 of them we want to be present and up to date. So that's basically checking here. And then we go back from the route once we have basically the primary, the secondaries listed out, the healthy targets, up to date nodes, and we go back to the coordinator. At this point, we set up the transaction for the write. And transactions are managed by Prefect. They are per write, basically. Per request, it's not really anything persisted anywhere. They're only kept in memory in Prefect during the RPC. So the coordinator has a method for registering the transaction, which does exactly set up the quorum requirements that we were discussing earlier about, like how many nodes need to agree on the write to go through. Somewhat different from maybe other replicated systems is that Prefect actually doesn't really enforce a minimum replication, like minimum number of nodes that the write needs to be persisted before it accepts it. So while we are selecting nodes that are healthy and up to date, if there happens to be, usually we would want to have 5 replicas, but we only have 1 up to date and healthy, we will happily accept a write only on that 1 node. So there's no requirement, so to say, that you need to have a majority of nodes that host the replica and participate in the transaction. With the transaction setup, it's injected in the context, so it carries through GitLab in the metadata. And this part we are again rewriting the repository messages and then proxying the call. Once the write finishes, so in Gitalis it goes into some handler. Let's say I'll pick some handler from here, for example. Let's say we pick operations service. I'll just create branch here. So what happens here is basically that all of the Gitalists, they receive the same request and they all process it at the same time. And they all build their own, for example, in the case of commit files, they would all build their own commit. And once they have the commit ready, they're going to try to update the reference through Git. And at that point, we have a reference transaction hook, which basically catches all of the reference updates being done and calls back to Gitali. So the hook logic is sort of set up in the Git. It goes through the command factory, which contains all of the setup logic for Git and other commands. And as part of it, we have an option that allows to configure the hooks. So here, for example, this is configuring codebase to have an reference transaction hook then. I think the exact machinery here gets a bit complicated. So on a high level, basically we pass through, let's see, we have a graph for the high level actually. Yeah. This part. So on high level, what happens basically the operation service. Okay, let's go to the Git case first. So with the hook configured, Git runs its reference update, and it calls the reference transaction hook that we've configured for Gitali, which invokes Gitali hooks. Gitali hooks is just a small binary that is single sole purpose is to call back to Gitali, and Gitali then contains a hook service, which is, I can show the proto actually, probably easier, which is just a service that contains an RPC for all of the various hooks that we have. So pre-receive, post-receive, update, reference transactions. So in this case, Git invokes Gitali hooks, which calls it the hook service. And hook service then runs whatever hook logic we have. So there's pre-receive hook, which does access checks with GitLab Rails. And then the one that we are talking about here is reference transaction hook, which then calls back to Prefect. And Prefect has a service for then receiving these votes from the writes. Transaction service. So the transaction service is basically just taking votes in and some other control it. You need to cancel stop that transaction. The vote is basically just, it identifies the repository which we are writing to and the transaction ID. Prefect, as we mentioned earlier, Prefect is keeping an in-memory state of all the running transactions. And it tells Prefect also like which node is now voting. And it contains the hash of the update. So we don't actually send, basically we just need to make sure that all nodes are making the same change. So the way we do that is that you get a list from Git in reference transaction hook of all the updates that are about to be performed. For example, reference A is being updated from this old value to a new value. And we take that list, basically we just hash it and send it to Prefect, and that's the vote of the node. And Prefect then takes these into transaction service. That we have somewhere in the transaction service, which is hosted here. This is one of the services that is not proxy it, so Prefect takes this in, handles it directly. It delegates to the transaction manager, which then basically adds the vote the node sent, and it waits for all the votes to arrive. So once you have, basically, if you have 3 nodes voting, it will wait for 2 nodes to vote in the same manner, and if it has enough votes to say that, okay, this is going to go through, then it releases the nodes to proceed. If the votes differ here, and Prefect decides, for example, the primary votes differently from the primary votes differently than a secondary. The secondary basically receives a message saying that you voted differently. Do not apply the updates. It will abort the updates, so no reference changes are made. And then at that point, we start returning from the hook service. We basically return a response to Gitali hooks. So Prefect returns a response initially to hook service, which returns back to Gitali hooks, which goes back to git receive back, and then that basically fails the command invocation in Gitali true, and we get the error back through std. And then the RPC handler in Gitali will return, go to Prefect, and mark it as a failure. If they all vote through, then they will just do the same process, although apply the reference updates on disk and return the successful code back up the stack. Prefect then checks in the coordinator. Yeah. So the responses are returned back to the proxy of Prefect, and Prefect then every time it creates a transaction and write in general, routes are write, it creates a transaction finalizer or a regular finalizer, a request finalizer for the write. So the finalizer is invoked every time proxying a request is finished. So in this case, for example, proxying a transaction, we can go first to, so this is the actual function, but should use, yeah. So here, before we return to the proxy, we also set up various other things, for example, the finalizer. So the finalizer is then invoked in the proxy, and the finalizer invoked in the proxy at the end runs the logic that records all of the writes and decides if we need to replicate or not. In this case, for the transactions, they look at some state whether we need to actually replicate. So there are some cases where, for example, if there was no recorded writes and the primary exited without an error, then in this case we don't replicate. If there was a write that was performed, but the primary was not there, we know that actually it couldn't go through, so we don't replicate. Overall, we are just looking at the different votes that came out, whether the votes were different, if there was errors or anything else that indicates that we have to replicate, then we do mark the nodes basically as outdated and indicate that we should schedule replication for them. The logic basically, the complete logic to decide whether a node is up to date or not after a write lives in the get updated and outdated secondaries. And there is quite a lot of convenient actually metrics and logging here that we can see usually why that happens if the node is out of date after a transaction. So once we have the up-to-date and outdated nodes, there's the request finalizer, which does all the metadata updates in the database. It takes the information that we just looked at, basically whether which nodes are up to date and which nodes are considered outdated, and updates the metadata accordingly. So if they are out of date, this is the part where Prefect always schedules replication jobs for the repositories. And it's one of the, I think, currently open issues that we do this always. So in the end, if you have a lot of writes coming through, we always schedule more and more jobs. But in general, how Prefect tracks the up-to-dateness of a repository is the generation numbers, which is incremented here for the up-to-date repositories. The generation numbers are basically, let me get the database state up of it here. The generation number, so we have two tables basically, which we use to track repositories. We have the repositories table, which is sort of like what you would imagine. It contains all of the repositories that are on the virtual storage and contains the expected state of the repository. So, you know, this is basically the expected write count the repository should have. The generation number that we are implementing here is it's very simple way to track repositories up to dateness. It's basically counting the number of writes the repositories that has accepted since it was created. And if a replica doesn't successfully apply a write, then we don't increment its generation number. So only the up-to-date nodes that successfully apply the write will get their generation number incremented. Prefect then uses this for deciding that, okay, this node hasn't applied a write, I know another node has, and schedules replication based on this, and also route request based on this. Once the generation increments are done, the metadata updates are done, the write would be finished, and the proxy returns the response to the client. So that's basically the path of transactional writes. There are a few special cases. I guess we could talk about those, but let's, I think, talk more about the metadata that we have first. For the database state that we have, so we have a document actually also in the docs folder that describes some of the workings of it. So there's one table which is for the repositories table, which includes basically like records the expected state of the. So this just includes like a table from basically like the external storage name and the external path of the repository that we expose to GitLab to replica path, which is then actually the storage path we use on the GitLab servers. It contains the primary of the repository, the generation number, which is tracking the number of writes accepted into the repository, and also the repository ID, which is how Prefect identifies individual repositories. There's another table called storage repositories, which contains mostly a similar piece of information. So the repository identities are actually sort of deprecated fields, but the repository ID is what just links it back. So the storage repositories table contains replicas of the repositories. So the repositories contains the actual repositories that we are supposed to have on the external repositories, so to say the virtualized repositories. The storage repositories table contains the replicas of the repository, basically, which were like replicas exist for a given virtual repository. It just contains the storage of the storage name, the backend node that contains it, contains the generation number. So this is how we then determine whether a replica is up to date. We compare the generation number of the replica to the generation number of the repository. So has it acknowledged the same amount of writes as we've observed in Prefect. This then contains some other metadata we can get to later as well. So those two tables actually are enough to sort of have a catalog of all the repositories that we have on Prefect and whether they are up to date. It's just basically looking at the external identifiers in the repository message. So storage name is the virtual storage here. The relative path here is the relative path here. Generation was the version number. And replica path is then where we are internally storing the repository. So this is something we skipped when we were initially talking about the routing. I think I'll cover that now. So previously, what Git cluster did was basically that when a call was coming in from a client, the client actually decided the relative path of the repository. So the clients were saying where to store repositories on the disk, and Git cluster would do that. That had a lot of issues with, for example, lazy deletes. So if we issue a delete for a path, but then the client wants to recreate it, they start conflicting. There were a lot of races. So what we did was that we abstracted the actual path away from the client. So Prefect now decides the paths where the repositories are stored. And this replica path then stores that path where the repository goes. It's overwritten in the same place as the storage. So if we go for the rewritten message, it's also overriding the relative path of the repository with the relative path that is given from outside. And that relative path again comes from the router as well. So the router, if we look at the accessor, for example, by the time we are getting the updated up-to-date storages here in the router, we are also getting the replica path, and that's how the translation is done. So the router gets the translated path name and sends it forward to the proxy, and the proxy then relays it to the Git list. As we sort of quickly covered, there are some operations which are actually captured by Prefect that are not handled like the others. These are mostly rename repository. We can actually have the list here in server go. So these ones here. So there's remove repository exists, and delete object pool. And there is also a rename repository which doesn't exist in the list due to the feature flag, but it exists here. These are handled specially, mostly because they are somewhat dangerous and difficult to replicate. For example, the renames, how the metadata updates happen, where basically that we first apply the operation to the disk, then later on update the metadata. So if you are renaming a repository, you first move the repository on the disk, then later try to update the metadata. And if there's a failure in between, then you've lost the repository. So Prefect handles, for example, rename repository to avoid renames. So the replica paths are static. They don't change. Even if the client issues a rename, it's just a database operation in Prefect. Nothing is moved on the disks anymore. And that's actually the distinction between the relative path and the replica path, is that the relative path can be changed by the clients. Replica path cannot. It's set by Prefect and it's persistent, never changed. Likewise, there's the delete repository, which is handled separately. Remove repository. It has the same issue. It first goes to the if you went through the proxy logic, you would first issue the delete on the disk, delete repositories, and you could fail updating the metadata, at which point Prefect would believe that there are repositories that actually don't exist on the disk. And that could then cause issues. For example, if you try to uphold a certain replication factor, you believe there's a replica that exists, but it actually doesn't. So you might accidentally delete the last replica of the repository. So this is also to avoid these sort of changes. The deletions are done differently. Basically, Prefect just deletes the database record. As soon as the database record is deleted, the repository is logically deleted, and then it still tries to clean up the disks, but it's not really guaranteed that it always works out. But yeah.
so if it deletes it from the database and there's a possibility that it doesn't delete it from the disk, does that mean that that repository exists on disk forever?
Right now, yeah, there's nothing
Okay.
that deletes the repository. There was a discussion about a cleaner that would basically walk the storages and remove stale repositories that were deleted from the cluster, but it's not finished yet.
Okay, thank you.
So that's actually the repository path. I mean, we're almost at time. I mean, I don't mind actually talking through the background functionality of Prefect as well. But do you have any questions at this point?
I had one other question regarding the database, the storage repositories table. So that is holding information about replicas, right?
Yeah, storage repositories holds replicas.
So if in Prefect we have two replicas and one primary, does that mean that we have the repository ID twice in the storage repositories table?
Yeah, you would have the repository ID twice. It's a given replica would be identified by the repository ID and the storage.
Got it. Okay, thank you.
Sorry, wouldn't it be 3 times? Once for primary and then the 2 secondaries?
Yeah,
3 rows.
Yeah, did you say 3 replicas? But yeah, each replica has 1. So if you have a primary and 2 secondaries, then you have 3 rows, right?
Got it. Okay, so even the primary is in here.
Yeah, the primaries, all of the replicas that exist on the disk should be here. And then we just separately have the name of the primary storage here. So it's just referencing that, okay, this storage is the primary and all the replica records are in the storage repositories.
Understood. Thank you.
Thanks, Will.
I have a question.
Yeah.
Okay. I was just wondering, how does the synchronization work with gRPC streams? Like you have multiple nodes and you have multiple streams open with the client and you're proxying also at the same time. So.
On the gRPC level, each of the RPCs, they are separate streams, HTTP2 streams, right? So they go on the same connection, but they are separate streams. Let me actually dig into the Prefect proxy handler. I think most of this happens here. So for each of the destinations that the router decides. So for example, the router decides here that, okay, we have those 2 replicas we want to proxy to, and we also have the primary. So we take the primary, we open a new stream, and then we open 2 streams to the clients. So these are always new streams on the same connection to the Kitalis. And then there's the proxy contains basically a codec that allows it to sort of transparently just stream the call on these client streams. So it's actually handled mostly by gRPC.
All right. And how do we multiplex these multiple streams that we have to the client? Like we have the primary and secondary, right? And the client in the end expects only one stream coming through, basically.
Yeah, it gets the one from the primary.
Okay. Okay.
So it's somewhere here. Receive secondary, forward primary to clients. Yeah. So this part is then actually forwarding the response back to the client, and well, we call it somewhere. Forward. Yeah, we call it here basically. So the primary stream goes directly to the client. There's some logic in still that, you know, in case there's like a failure, that we can overwrite the response at the end of the trailers. But yeah, this
and then
all of the
sorry to jump in.
Yeah.
I see another point of synchronization for like when data gets changed, and this part Semi covered it, but it was a little fast. And It was the Git transaction hook, which so whenever we want to update a reference, there's a feature in Git where we can open a transaction, and then so each Gitly node, on repository A, let's say we're changing a ref, and each Gitly node, each Git on each Gitly node will open a transaction for that repository, and then and then it will fire off that hook, which talks back to Prefect, and so all the updates, it will wait, it will block until the votes finish. So that's another part of the synchronization.
Right, yeah, so the waiting happens in, so basically what happens is that you have the parent span of the whole RPC, and then the voting happens within a span inside the parent, right, goal. The transaction server in Prefect synchronizes everything, so it waits for the votes to arrive and only releases them after the votes have arrived and say that, okay, let's do this change. And at that point, the primary can return as fast as possible, basically back to the client. It could be that some of the streams still keep going, but the proxy itself still waits for them. Yeah, maybe we'll just cover quickly some of the background code routines we have. So one of the main background routines in Prefect that we have is the replication handler called the Replication Manager. I think it was replica matrix. This is something different now. Replicator, MGR, I think, yeah. The Replication Manager is launched in the background for all the prefects. They basically go to the database and fetch replication jobs, which are scheduled at the end of the write calls in the weakest finalizer. And there's also another component in Prefect, because it could be that one node is down, for example, during the transaction. So it could be that the replication jobs also get dropped eventually. We don't keep them forever. So the node may stay out of date. So we have another component called the Reconciler, which is this fine piece of SQL here. And what it does is basically, it looks at these tables, storage repositories, the assignments, and the repositories tables, sees which, where do we expect to be have up-to-date replicas, and just schedules replication jobs to do that. So it's basically the logic is something like, is the generation the same for the replica in the storage repositories table as the repositories table, and should we have it based on the assignments? Is this node supposed to have it? And then scheduled replication jobs. This happens periodically based on configurations, 5 minutes by default that we checked. And then the replicator runs through the replication jobs one by one. The concurrency is quite limited at the moment. Prefect basically runs one worker for each virtual storage by default. And so here it first picks the nodes that it should do. It's basically going through the queue periodically with some backup. Takes a job. Based on the job's what the job actually says that it should do, it picks a proper method, which is replicate, destroy, rename. We've been sort of moving away from rename jobs. They're not scheduled anymore by Prefect. Also destroy, I guess, is going away soon. Replicate is that's the only one. So the replicate is really just taking a job. The job says replicate from this GitLab node to this GitLab node, this repository. And with that in place, it basically calls the other GitLab node to do a fetch from the source node to the repository. And once it returns, if everything is fine, it will just mark the update the generation of the target repository match what was replicated to it just now. And this is concurrency control, so there's only one fetch ever in progress and whatnot. So should be no sort of races there. So the replicator is the one bigger background component. One of the other ones that we added more recently is the verifier, which is, so we sort of covered some of the metadata inconsistencies that we can have. Basically, if you run an update on the GitLab node and you cannot update the metadata for any reason, say a crash, database unavailability, the metadata will be inconsistent with what's actually on the disk. So the most recent background code routine we sort of have for addressing that was then added here. It basically runs through the repository records periodically, checking whether they still exist on the disks of the Git list, the replicas that should exist, and deletes them if not. It doesn't actually understand the content of the repositories though, so it can't identify all of the cases, but the more frequent ones where actually there's a missing record or an invalid record rather. That could happen if someone deleted the repository manually or if there was a disk failure, or the most, I guess, pressing one is that if you have a complete node failure and you return the node, this will delete the invalid records from the database and then triggers replication again. And I think the final two bigger points. We didn't go through the election logic at all yet, so I would probably cover that quickly, and then the health manager. So there's one more background code routine in Prefect. This is how we health check the GitLab nodes. It basically runs every second. It pings all of the backend GitLab nodes and just updates the database saying whether I was able to contact them or not. And then from the consensus of Prefect nodes, we can sort of determine which GitLab would be the best to be the primary. So if all three GitLab nodes agree that this GitLab node is healthy, then that's probably a better primary than one that we don't, like only one of them can contact. The primary election logic happens lazily, only when it's necessary. So basically during writes, when we are routing a request. So the get primary call here, an accessor for certain accessors that need to be routed to the primary. There's a couple of them, mostly because of inconsistencies in the data. I think it's, yeah, it's mostly like disk sizes of the repositories, because that can change between the replicas. But then also the mutators need the primary. So the mutators always get the primary before routing. And the primary election logic is then here in the repository. So the logic is something along the lines that basically the primary needs to be healthy according to the health checks of the GitLab nodes. And the primary will always be an up-to-date replica. So we don't ever elect an outdated replica as the primary. The primary is only changed if there's actually a reason to change it. So if the current one is recorded somehow unhealthy or outdated, we would immediately change it. Yeah, actually, that's mostly what there is to the primary. It happens per request when the primary is needed, only when it's needed due to the GitLab being outdated or unhealthy. And then updated, and it remains the same until we can either change. There's no demotion logic or anything. So if the primary, like there's no valid primary to update to elect, then there's no primary change to be made.
If the primary is failed for a given repo, does that get updated to like permanently in the database?
Yes. So the schema contains the primary in the repositories table, right? So here, the repositories table contains the primary, and if the primary needs to be updated, we basically set the primary column here on the repositories table, and then it's persisted. And every subsequent write would use the same primary until, again, there's a consensus that either this Gitali node is unhealthy or we need to change it because it's somehow out of date.
So is it possible for, like, if a node fails, and now maybe it's a little bit unbalanced because a lot of the primaries have been rewritten to another node? Is that just supposed to be, is there any way to equalize that later, or is that just, over time maybe it stabilizes?
Yeah, and not really. So it can completely happen that if a node fails and another node fails, and you have the one last third node available, all of the primaries move there, and once the other two nodes come back, now all your primaries are on the last node. There is nothing rebalancing the primary status of the repositories.
Okay.
So if the node then went down, then they would be probably equally split about randomly on the two remaining nodes, but there's nothing overall like balancing the primary status of the nodes.
And that would really only affect write distribution, right?
Yeah, it's so if you're doing a write, most of the time you would anyway be writing to all of the three replicas, because we do the writes in sync with transactions. There is a difference, is basically that the primary runs the Git hooks, the followers don't, the secondaries don't run them. So there is some extra load basically that happens to land on the primary, and also there are some cases where the repositories still get out of date, out of sync through writes, through various issues or bugs in the transaction logic or missing transaction logic completely from certain RPCs. So they do end up getting like more load. I think the one sort of remaining that can be sort of surprising in the request flow is the connections between Gitalis and Prefect are multiplexed. So there's a two-way gRPC. There are two gRPC sessions running on the same connection. One is from Prefect to Gitali, and the other one is from Gitali to Prefect. Prefect to Gitali runs everything, basically all the client, like the proxy client calls and whatnot. The Gitali to Prefect gRPC session is only used for the voting traffic. So it's basically, you cannot do bidirectional gRPC, like you cannot have the client act as a server. So you couldn't issue RPCs from Gitali otherwise to Prefect without opening a new connection, which turned out to be difficult for various reasons like DLS and such. So the point here mostly is that there's actually also a gRPC server in Prefect that runs at the end of the Prefect initial connection to Gitali, that Gitali then uses for the transactions. It's something to just keep in mind. It's not plain TCP that's going in between the two nodes. But there is a custom multiplexing going on there. And for the transaction flow, it's mostly relevant if we go for the Gitalis transaction implementation. We can look at the reference transaction hook. And what it does is that it ends up here, and then it has this sort of magical get transaction client field, which is referring to back channels. And the back channel is basically the multiplexed connection between the back channel is basically the gRPC connection back to Prefect from Gitali on the Prefect initiated connection. So going back to the client, but the client is the server in this case. It's handled in the server. basically here somewhere. So what happens is that when Gitali receives a connection from Prefect, it, instead of just accepting gRPC call, gRPC connect session, it just creates a multiplex session, opens one back, gRPC session back to the Prefect and passes down that connection in the context. So what we basically get here is we're getting the private connection from the context. And not, I guess, a great detail, but something to keep in mind. Do you have any particular questions, like on the overall how things fit together, or higher level, or some more detailed?
I guess I have one question. So you mentioned that there's the virtual storage and like the actual storage, right? So process-wise, like, do you have like 3 Prefect servers and 3 storage servers that are running Gitali? Like, from a process level, how does that look from an infrastructure point of view?
Yeah, so the usual deployment would be something like 3 Gitalis and they're fronted by 3 prefects. The virtual storage is just a name in the configuration that had been set for the collection of backend Gitali nodes. So I'm not sure if I have something in mind. Maybe I have something here, or maybe not. So here, for example, this config would be the same for all of the prefects. So you have 3 prefects, they all just have a virtual storage called prefect, and then they have these would be the internal storage names on the Gitali. So the Gitali nodes would be configured with this as the storage name.
So prefect gets 0 to 2. They will be, what process will they be running? Will they be running Gitali process or prefect process?
Yeah, these are Gitalis basically.
Oh, okay.
So
understood.
Yeah, it would be better like this.
Got it. Okay.
But yeah. So the sort of like a higher level picture there is that previously there was only Gitali, and what Prefect aimed to do is that it's just plugged in between. So the API is the same. So the virtual storage is basically what would be a storage name on a Gitali. And Prefect then handles internally the fact that there are multiple storages internally and it just routes them correctly.
Okay. And how does Rails know which prefect server to contact, since it has 3 prefect servers for each storage, right? Or am I misunderstanding?
Yeah, any of them can be contacted. So Rails does it through a load balancer. So Rails calls a load balancer that goes to one of the prefects. They all have the same virtual storage name, and then they will route to the backing Gitali nodes.
And the load balancer is a dumb load balancer like Nginx, or can it be, is it a specific load balancer?
It's sort of any TCP load balancer.
Got it. Okay.
All right, so we are over time. So I think if there are any remaining questions, feel free to put it on this doc, and then maybe we can find another forum to answer any questions that people have. Yeah, thank you, Sammy, for doing that.
Thanks for attending, and I hope I managed to somehow explain it. I mean, it's a bit difficult. There's so many moving parts in Prefect, but I hope
there's a lot going on in there.
Yeah.
Yeah, if we need any kind of follow-up, then yeah, I'll try to schedule something. But thanks everyone.
Thanks everyone.
Thanks, Sammy. Thanks, everyone.
See you.